Okay, so this topic is on axial load and potential energy. So if axial shortening prior to buckling is neglected, the distance delta due to flexural action is given by delta is equal to L minus A. So if we have this simply supported beam with the original length L, this shortening delta plus A is then L. Or in other words, delta is equal to L minus A. We know that this curve y of x is equal to the integral from 0 to a, and inside the integral sign we have 1 plus y prime quantity squared dx. So this is the arc length of this beam. However, this can be quite comprehensive to integrate, so we can do an approximation. So we can approximate this quantity 1 plus this curve length derivative of y squared. We can approximate this using the Maclaurin series. Or the binomial approximation. The binomial approximation says that if you have this can be approximated as 1 plus 1/2 y prime squared. So using this and that the length of the curve is L, then we get, so using this and that the length of the curve is L. Then the integral from 0 to this a of 1 plus 1/2 y prime squared dx is equal to a plus integral from 0 to a of 1/2 y prime squared dx. This is then equal to L minus integral from 0 to a 1/2 y prime squared dx. This gives that delta is equal to L minus this integral from 0 to a of 1/2 y prime squared dx, which is equal to integral from 0 to a of 1/2 y prime squared dx. Assuming a is approximated to be L, so we get that delta is then equal to the integral from 0 to a 1/2 y prime squared dx. So the loss or change in the potential energy of the critical load is given by, so the loss or change in potential energy of the critical load can be equal to V is equal to minus P times this delta equal to minus P over 2 integral from 0 to L y prime squared dx. Hence, the potential energy becomes pi is equal to u plus this v is equal to ei over 2 integral from 0 to L of y prime prime squared dx minus p over 2 integral from 0 to L y prime squared dx. If you take the variance of the potential energy, and this must equal 0, we get, so the variance of potential energy must equal 0. So variance of pi, this is equal to the variance of u plus v. This is equal to 0. So we get that the variance of pi is equal to the variance of ei over 2 integral from 0 to L y prime prime squared dx minus the variance of p over 2 integral from 0 to L y prime squared dx. We can use Leibniz rule and take the variance under the integral sign. So this variance is then equal to, this is of course ei over 2 integral from 0 to L of the variance of y prime prime squared dx minus p over 2 integral from 0 to L of the variance of y prime squared dx. So we get variance of pi is equal to ei over 2 integral from 0 to L of 2y prime prime times the variance del y prime prime dx minus p over 2 integral from 0 to L of 2y prime del y prime dx. Now we need to do integration by parts 2 times on this and 1 time on this. So we get variance of pi is equal to the 2's cancel. So just rewrite the equation above. You get ei integral from 0 to L y prime prime del y prime prime dx minus p integral from 0 to L of y prime del y prime dx. So if we do the integration by parts, we get the variance of pi is equal to ei to y prime prime. And the rule is that we take away 1 prime from the del operator. We get del y prime, insert at 0 to L, minus ei integral from 0 to L. I could take this both integration by parts in one go, but I take first do one integration by parts and then another afterwards. So I transfer this derivative over to the y. So we get y prime 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 del y prime dx. And the integration by parts done on the other term, we get minus p. So we have y prime del y from 0 to L minus which is plus, integral from 0 to L of y prime prime del y dx. Okay, so now we only have to do integration by parts on this to get it on a strong form. So we have del pi is equal to ei y prime prime del y prime from 0 to L minus ei y prime 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 del y from 0 to L minus it's plus, integral from 0 to L of, so I transfer the derivative over to the y, so we got y prime 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 del y dx minus p y prime del y from 0 to L plus this integral from 0 to L y prime prime del y dx. Okay, we know that for the boundary conditions, we know that del y of 0. This is equal also del y at L, which is 0. Then, then we know that is minus ei y prime 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 del y from 0 to L, 0 to L is 0. So this part is 0 because of the boundary conditions. And we know that minus py prime del y, 0 to L, this is 0. So this part is 0 because of the boundary condition. We are therefore left with this part, ei y prime prime del y prime from 0 to L plus this integral from 0 to L of ei y prime 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 plus py prime prime del y dx. And since these terms equal 0, must equal 0 simultaneously, so since these terms must equal 0 simultaneously, we get that ei y prime prime at L is equal 0, which means that y prime prime at L is 0, and ei y prime prime at 0 equal 0. So y prime prime of 0 is 0. And these are the natural boundary conditions. Uh, our governing equations become ei y prime 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 plus py prime prime is equal to 0. That's because of the fundamental lemma of calculus of variation that says that this must equal 0, since del y is arbitrary. We don't know if that's 0. Okay, and this is as stated in previous lectures. This is the Euler-Lagrange method. Okay, and we will do an example of this.